So five, 4, 3. Hi, welcome to the Semantics lecturette about relative clauses. Relative clauses are sentences that modify other constituents, notably noun phrases. And what we're going to try to understand is why, if these are modificational, why they have the same semantics as something like an adjective, when they aren't built the same way. Now, it's been established for over 60 years that relative clauses are basically descriptive phrases that behave like other modifiers. So if we take an adjective like the delicious crepe, delicious gives us a property of things, it combines with the property of being a crepe, and you get the thing that is a crepe and delicious. But if we used a relative clause, the crepe that is delicious, then it essentially means the same thing. We have something that's in the set of crepes, and the set of thing, and something that's also in the set of things that are delicious. So, setting aside things like tense and verbal stuff like that, relative clauses mean the exact same thing as adjectives. And even if you include the tense stuff, we can say that they both denote properties of individuals. So if a sentence, if a relative clause denotes a property of individuals, the question that we want to ask is, how? If the relative clause contains a sentence, which is a saturated expression, how do we end up with a property, which is unsaturated? So the trick is essentially that we will employ a new rule of composition that builds off of the fact that we have a relative pronoun and employs variable binding to essentially take an expression and add an argument to it. So let's take a look at the syntax in 20 of the crepe which was delicious. Now this is just focusing on the CP. And if you look at the maximal CP projection, which we've listed as CP max, right, that's going to be a relative pronoun which has an index, and then a complementizer, that, and then the sentence, which will have a trace that is linked to the relative pronoun and created by movement, and then the VP, which was delicious. That's a straightforward syntactic structure. And these are co-indexed, so we can tell that they're linked together. And so far so good. So the question then is, how do we get this to have the same meaning as this? What is the meaning of this verb phrase? Well, it's going to be the function that gives you 1 if something is delicious and 0 if not. And that's what we want here. So essentially, what we want to do is add all this structure and have the exact same result. Well, what are we going to do? Right. Well, start with this trace. What is the meaning of the trace? Well, a trace has an index, and we know how to interpret terminal nodes with an index. It's a terminal node, it has an index, right? We can use the pronoun rule. So we can effectively treat traces as a variable. So if your assignment is G, then the meaning of this will be G of 1. And then we can just plug it in to our verb phrase, and we get our sentence. And that will be of type T. And so far so good. What this means is G of 1 is delicious. But that's not what we want. We want to undo this to get another property. And so how are we going to do that? Okay. So, well, we can start with that. Now, in Hyman-Kratzer and in some of the older theories, the complementizer doesn't really do anything. In newer theories, it will do something, but we're going to save that step for another time. So what this does is nothing, and so you can just take it out completely, out of the LF, or you can give it some kind of identity function of type TT, and then it will just give you what you put into it. So far, so good. Now, we end up with delicious of g of 1 up here. Now, what are we going to do about that? Well, we have this which. We have which has an index, but we're not going to interpret it under the pronoun rule. We can't, in fact, because if we did, we would get g of 1, and we can't combine that with this. This is of type T. This would be of type E. We would be at an impasse. So we have to interpret this somehow, and we also want to interpret it in a way that it creates a property. And for that, we will need a new rule, and this rule is called predicate obstruction. And the rule will rely on the assignment modification. So the rule is listed here on page 5. And essentially it says that if alpha is a branching node, and its daughters are beta and gamma, such that beta is nothing but an index, then we can interpret for any variable assignment that this will equal the property abstracted over it, where the index is replaced by the variable. What? Right, this employs a logical notion called abstraction, which we've seen before with sets. And here we're doing it with predicates, where we take an expression and we make a predicate by slapping on a lambda. So in predicate logic, we would have something like this, delicious of x, and then we'll just throw on a lambda. And as long as this lambda expression is represented by a variable in the value condition, then we're good to go. Right? That's the condition for lambdas. They have to bind something. However, we don't have delicious of x, right? We have delicious of g of 1, or x sub 1 if you like. You can put it like this, or like this. The result is the same. There's an index. So how do we turn this into an index? So we'll leave it as g of 1 for now. How do we turn that into an index? Well, that's where the assignment modification will come into play. Remember, the assignment modification will say we need this to be x. And an assignment modification says, oh, we can specify that whatever index we want points to whatever entity we want. So instead of saying g of 1, we modify it so that g will map 1 to x. And then whatever 1 was going to map to is gone, right? We've replaced it. And so we've replaced it with x. And so what is this going to be? This is going to be x. And so now we have our x. So instead of saying delicious g of 1, we say delicious g modified so that 1 maps to x of 1. And then if we plug that in, we get x. So now we have delicious of x, and we can slap a lambda on it. So what we need then is a rule of composition that will do that, and predicate abstraction does that. So how does it work? So we have our binder, lambda 1, right, or the index 1. We interpret the relative pronoun as nothing but a binder. And we have our expression, delicious g of 1. So the rule interprets it this way, right? We can read the rule. The alpha, the meaning of alpha under A equals what? Lambda x in d sub e. So we're slapping on a lambda. And this is step 1. We just add the argument. Step 2, we copy the value condition of gamma. We're just going to copy it wholesale. So this is step 2. And then for step 3, we're going to modify the assignment so that instead of g of 1, we have g such that 1 maps to x of 1. And that's going to be step 3. Now, we have a function and an argument. We can run it through. Right? And since we've specified what 1 maps to, well, we know what that's going to work out as. 1 maps to x. So we plug 1 into this, we get x. And so we can do this as a kind of 4th step, you could say. Delicious of x. And look, we've got ourselves a property. We've added a property. We have abstracted over this sentence and we've got our property. And now we can conjoin that with whatever we want. So we can specify that this is the predicate abstraction rule and that it is of type ET. And so the handout will go into more detail about the motivations for these steps. And there'll also be a handout with exercises where you can practice the abstraction step. So you can think about it this way. This is how it works. The shortcut way, the shortcut way is just to find whatever has the index in the expression and then slap a lambda on the front and replace the index with the lambda's variable. That works too. That's the shortcut way. But what I've done is explained actually why this works, why you can do this, and how you can do this in a semantics that has indices. So that's the predicate abstraction rule. That builds us relative causes. And we'll be using this rule throughout, whenever we need to bind something. And the lecture will talk more about variable binding and covariation, and it will be very useful. But for now, that's how relative causes are built. And we'll see that a lot of things get built in the same way.